All right. Hello. Thank you all for coming today. We're so happy to have you here. It was quite the keynote to get everyone started this morning. I definitely would not want to read Crashing and Burning, Learning How to Fly a Plane for Dummies. For those of you who are watching our stream, we're happy to have you here as well. So my name is Alison Cossette. I work for Neo4j, and I'm here to talk to you today about life beyond the vector. So just to figure out who's in our audience, is anybody here currently working with vector databases at all? A little. Anyone ever work with a graph database? All right, good to know. Is there anyone working on RAG applications at this point? A few. All right, so you're all in the right place, so that's good. So what we're going to do today is first we're going to talk a little bit about graph RAG, which is retrieval-augmented generation with graph. We're going to talk to you about how to produce an optimal data set for that RAG application. We'll show you a little bit about actually logging your interactions and the value that can come from that, as well as ways that you can use data science. Any data scientists in the room? No? A few. There we are. They're down in the middle. But also how you can leverage your current data science staff to help you produce positive and good outcomes with your applications. So just as an overview, the grounding and retrieval in your grounding and retrieval augmented generation. So we'll dive into this in detail, but for those of you who may not be working with RAG applications, roughly what we're looking to try to understand is when we're working with our, say, your chat GPT. So right now you have a user prompt, right? Everyone here has used chat GPT or something similar, I assume, yes? Okay. So you put in the prompt, the GenAI application, whichever one you prefer, gives you an answer and you get a response. But what retrieval augmented generation does is it takes your response and then it hits an external database to ground that response. So rather than using a general language model, which is what these are meant to be, we want to actually improve the information and have it grounded in something specific to you and specific to your use case to get a better response. So what happens is the information from the data set is added to that context of your original prompt, and then it produces a new answer from the LLM. So the question is, what do you want to actually use for that external database? You can have something, right now we're going from this unstructured set and you create the vectors. So the vectors are the embedding, which is a numerical representation of that unstructured data. But when you use a knowledge graph and you use a graph database, you can bring in additional context to that answer. So you can bring in some relational database. You could bring in your structured data. You could bring in semi-structured data. And what we are looking to do is to really add to that experience of what is coming out in that response. So what I want to talk to you a little bit about first is what actually is a graph database and how does that work? So nodes really represent entities in a graph. So we can have a person, another person, and a car. In this case, there are relationships in and among these entities. These two people may know each other, they may live with each other, and one may drive the car and one may own the car. So the relationships represent these associations between and among each of these entities. Each one of these nodes or relationships can also have properties associated with them. So in this case, Andre and Micah own a Volvo with a V70. So the interesting thing here is that the information about the nodes and about these relationships are actually properties inside those. So when we think about vectors and we're looking at how we're actually indexing them, you can use, in this case, Neo4j, but what you want to be able to make sure is that you can actually index and search. And so we have different ways within our format that you can actually use this general indexing. You can use geospatial points, and you can use text, which is ultimately what we're talking about in our retrieval augmented generation today. So I'm going to talk to you today specifically about one instance that we built, which is something called Agent Neo. So in Agent Neo, what we wanted to be able to do is we found that ChatGPT and others were very good at some general information, but specifically for our graph data science, folks are having a harder time getting answers because people don't go to LLMs just for translation; they go to them for information. So how do we give that information back? So in our case, we built Agent Neo, and it's an LLM application that was built specifically to answer graph data science questions. We went through and we grounded it in our documentation as well as some community information. And we built a basic Streamlit app with LangChain. And we logged the conversations in the same graph database. And we'll talk about that a little bit. The code for this is all available online in GitHub. It's all open source. So if it's something that you're interested in building for yourself with your documentation, you can certainly do that. If you have questions, you can ask me afterwards as well. So what did we actually use? We used the entirety of the Neo4j documentation. We used the developer blogs and our support knowledge base, as well as our GitHub. So all of the code itself, as well as the documentation of that code and any discussion around that code, either in community or in the blogs, are all added in. We then created the chunks that were definitely a chunk size of 512. We used LangChain recursive text splitter, and then we used the embeddings. In our case, we used GCP. So when we think about this data and we wanted to go through and figure out how do we create the highest quality data that can go into this application. So obviously, it's really important that we have this high quality output, but a lot of times what folks are struggling with is they're new to building these applications, and we say, let's just take everything we have and we're going to put it all in and we're going to get a great answer. But what we want to share with you today is we have these 5 elements of high quality grounding. It needs to be relevant. And so obviously you want to have a relevant answer to what your question is. And we want it to augment. We want to bring something to the response that is not going to be in the natural language of the LLM to begin with. You need those outputs obviously to be reliable. The health and success of your application is certainly not going to do very well if the answers are not reliable. You want that data to be clean, and you want it to be efficient. So we're going to talk through a few different ways that you can build this data set or refine the data set that you may have to improve the output of your RAG applications. So one of the things that you can do is, and the data scientists in the room are familiar with EDA, which is your exploratory data analysis. What's in your data to begin with? How do we understand what we've made available to this RAG application? In our case, obviously, we work with graph. And so what we wanted to be able to do was to leverage what's possible with graph to inform that exploratory data analysis. So one of the things that we did first was to create a KNN similarity. It's similar, for here under the hood, if you want to know, it's actually Cosine Similarity that's running KNN here. And we wanted to create relationships among the most similar documents. What this allows us to do is then leverage additional algorithms such as community detection and centrality to understand of these documents, do we have similarities? Do we have clusters of documents? And are there certain documents that are more important and have a higher, what we call centrality or a rank within those groups? We use this to capture and document the node embeddings. So just like we have a text embedding, you can also have a node embedding. And the node embedding is the vector that represents the node itself and the additional items that it's related to within the graph. So what this allows us to do eventually is it allows us to curate this set and create techniques that work at scale. So what does that actually mean when we're trying to look at it? So this may look a little bit, there's a lot going on. It looks a little bit like a kid's cereal, a bowl of my children's cereal. But what we want to understand is when we think about vectors, right? We think about, in OpenAI, it's over 1,500 parameters. And just like in the matrix, when you're looking at ones and zeros and you're looking at numbers, they don't necessarily have meaning to you. And so what we wanted to be able to do was to take that high dimensionality and flatten it out and say, when I try to understand what's in my vector database. So this is a 2D representation of what's in the database itself. We went through and ran community detection to understand the clustering and the groups of documents that we had. The size also represents the content's page rank or its importance. So how connected is it to other nodes? How does it fit within that space? Because ultimately, right now, when you're looking at vectors, like I said, they don't jump off the page. They don't necessarily mean anything. And so you want to really understand what is it that we actually have in this data set. And so you might say, Alison, well, this is all well and good and it's a lot of colors, but how do I use it? What does it mean to me? So we zoomed in on a couple of different aspects of this particular visualization. And what you see on the left-hand side is you have a single community document cluster because they're all by color. And there's a lot of documents sitting on top of each other. You see that the size is a little larger. So that means that they're highly connected to each other. And on the right-hand side, we see a clustering of sort of overlapping communities, and they're not really distinct, and they have a lot of, different community colors. And so when you think about what is in your database, and if you think about the vectors that are representing those, do you imagine one or the other of these is going to give you a better outcome? So who here thinks having a lot of similar documents, like really close to each other, is going to give a good outcome? And how many folks think that a widespread? So who thinks that widespread documents are going to perform better? Any guesses? Lots of documents sitting on top of each other that are pretty similar. Or I have no idea, I've never seen this before. How could you possibly ask me that question? All right, option 3. Yes, what we're talking about is something that as developers you may not have seen as much. But one thing that you can do, and this is just a side note, look to the data scientists on your team to really help you dive into this and use this and understand what's going on in your data sets. So to answer the question for you, there's a case to be made for either, and we're going to walk through these as we go through. So we're still talking about exploring the data that we have. What we did is we went through and created these communities of the documents, so the ones that are most similar are all grouped together. And so then we say, okay, let's just look at them. Right? We know that we have a text chunk of 512 characters. And then we did some basic statistics. So what's the median average word length? Well, we clearly see in community 7117, not that I'm sure exactly what's in it, is we see that the average word length is 512. And so you want to understand just some basic QA of what the data is and has your chunker worked well. And what we found when we dove into this and we looked at those is we can see these large, JSONs of information that probably aren't going to give our users pretty good outputs. So this is a way that you can go through and clean some of the data that's in your RAG application. Because when you're building a RAG application, usually you're coming up with a certain number of relevant documents. Right? You might say, okay, go into the data set and return the 5 most similar values, vector to the prompt, and use that to augment. But if the 5 most similar happen to be an odd JSON, that's not really going to give you a better answer. So this is one opportunity you have to clean your data set. The other thing that we want to look at is highly similar text chunks. So what we're talking about here is that one on the left where we had the community where those documents were very similar and they were highly connected. One of the things that's going to happen is that We wanted to look, you see this first column, we've got the community number, and then we have the average similarity. So we know we have this vector and we create that similarity score. How similar are these items to each other? If all of the documents within that group are very, very similar, there's a high likelihood that they're going to be redundant. And again, it goes back to in your RAG application, you're pulling back a certain number of documents. Do I want really the same documents? So when we went in and looked at where we had that high similarity, you can see an example of what that text chunk looked like. Obviously, when we're looking at documentation, all of these come from our documentation. And there's certain information that you know is going to be on more than one page. And in this case, we're talking about how similar those are. And so if I'm only bringing back a certain number of documents, I don't want all the same chunks to be used. So then you're like, okay, Alison, that's fine. We've got all this redundancy. How am I supposed to clean that up? What is the technique for doing that? So when you store your information in Neo4j or in another graph database, one of the things that you have is we have a lot of flexibility. So in this case, we've got these individual documents, and each one of the documents has the URL of where we actually sourced it from. And you could just take one. If you're, let's just say you're in a traditional tabular database and you have all the rows, you could say, well, let's just keep the first one. But when you do that, you're going to lose the granularity of all the places that it's connected to. And so if you're using a graph database, you can use just this one short piece of code, node collapse. And what it will take is it'll take all of those documents and make them one occurrence, but it'll maintain that original connection to each of those URLs. And so it's a good way to handle going from one to one to one to many. So that's one way that you can increase the efficiency. So we've said, okay, we've got this RAG database. Before I go on, does anybody have any questions so far? I know graph might be new for folks, so I just want to make sure. Yes.
About similarity, what kind of similarity are you using? Cosine similarity?
Yes, so for those who are watching the stream, the question is, what are we using to calculate the similarity? In Neo4j graph data science, we use KNN, which is K nearest neighbor similarity, but under the hood, it is actually Cosine that's running that algorithm. So yeah, good question. Thank you so much. Anybody else? All right, we're good. So one of the other things we want to talk about is we want to talk about actually logging the conversation. So we're at a point where we've got a really good data set. It's nice and tidy. But what can we actually learn from logging the conversations with the LLM? So graphs enable explainable AI with your LLMs. So what it will allow us to do is we can actually say, okay, we had this particular question. We went into the graph database when that question was asked. We pulled in these context documents, and therefore this is what was referenced to produce a particular answer. And also with graphs, some of the interesting things we can do is that we can actually visualize the conversations with that context. So we can start to understand how are each of these vectors being used. So just so you know, in the graph database, we talked about the properties. Inside of that node, one of the properties is the text, and the other property is the actual embedding. So just so you know where that's coming from, those are properties within that node. So when we built Agent Neo, this is the data model. So for those of you who are used to seeing ERDs with your relational database, this is the graph version. So we can see all the way on the right-hand side, the document and the URL, which is that grounding that we have. But additionally, now we're going to talk about what happens when we actually add the log of the conversation to it. So someone will initiate a session, which we see all the way on the left. That session will have a particular conversation, and then there'll be a series of messages. So when that prompt is put in, then it'll hit the database and those context documents will be returned. And so now we create a connection not just from the prompt to the response, but also what were the additional pieces of information that helped form that response. And so that's what we're seeing in the relationship has context between the center message node and the document node. Questions on this diagram? Right. So this is what, again, like we said, it's like the ERD. This is the basic. But what happens when we actually put it into practice? So this is an example of what that diagram would look like. So we see the session in green, then we have the conversation in orange, and that first light pink is the actual first prompt in the conversation from the user. Then what happens is the LLM will go through and you'll see these has context. So what has happened in this case is that this first pink node has a prompt. And so we say based on that prompt and the cosine similarity of the retrieval, it's connected to these darker pink documents. Each of them are an individual document within the database. We have them noted with the number of the community that they're in, just for ease of understanding. And then we see that the person has a response to that. So just like you have a conversation with your ChatGPT, you put something in, you get an answer, you want to refine. And so then the last one that we see is the follow-up to that second input from the user. And what I want you to note is that some of those documents, those ones that are vertical in the middle, are part of the answer for both of those responses. But we see that the ones that are only tied to the first one are no longer relevant to that subsequent comment. And the new ones on the right that are only connected to that last pink node is where the conversation is going. And so what you want to start to see is you want to have an understanding of how is the application working? Where is it going? Are we answering the questions that we want to answer? And so when we think of this from a developer perspective, what it allows you to do is it allows you to see where is the application hitting more or fewer documents. Eventually that will be put on whomever is responsible for making sure those answers are appropriate. But you want to understand, how do I watch what's going on in the actual application? Okay. So this is where things get a little bit heavier and more for the data scientists in the room. But in this case, what we've done is we've taken the conversation, and across the bottom, we actually see the message sequence. And on the left-hand side, it's the different communities of documents. And what we're seeing here is it's the heat map, right? So the darker it is, the higher the count of documents from that group. And what we're watching now is we're watching how the conversation moves over time across the different bases of information that you have. So we see that in the first couple of questions, it's mostly these pieces in the middle, but then eventually the conversation starts spreading out into other areas of information, other communities of documents. And this is just one conversation. But what you can see is you can also start to see, where are conversations moving? What is actually happening? One of the challenges that people have right now that we've seen when they have their RAG applications is, how do I know what people are necessarily talking about? You can hit a particular vector, but by having this clustering in these groups and tracking this information, you can start to understand. I've said that like 9 times today. I don't know what is happening with me with this phrase. What you see is you can see where the conversations are going, and it will give you more of some business insight or some application insight. If you see that a conversation is spreading really wide, it could be an indication that there's a piece of information that's missing. Somebody's going to a lot of different areas to try and get an answer, and maybe that conversation is really long. And so then you can go back to your data set and say, do we have a gap here? So we want to be able to see, are people getting relevant answers? Questions on this image? No. Yes.
Not this image, but the image before. Is it some kind of way to ensure that the context will not become too big? So you get some kind of context overflow, because the context, in my understanding, cannot be too big.
Yes, eventually it can. A lot of that's going to be depending on how you've built it and which model you're using, but it can help you with that. In our case, I'll show you in just a second some information about how long they go, and that will be sort of in the way that depending on which model you're using. But yes, you can definitely get like spread of if you look at the actual vector of that prompt that has that longer context in it, but in this case, what we're looking at is we're looking at the actual context documents that were pulled in for each one of those responses. And so while the overall context might be larger, the context documents that are being pulled in from the database for that particular answer is going to be on a per prompt basis, right? So even if we see this one all the way on the right, it's in many different communities, it's still going to have the same K being returned for that particular response. Is that clear?
Yeah.
Awesome. Okay. Anybody else? Cool. All right. So we've got our RAG database. We've done some cleaning, we've done some understanding, we've looked for some redundancies. And what we want to do now is, now that we're tracking that conversation, how do we use it? How is that going to be helpful for us? So we have something where, especially for those who are new to graph, when we think about the conversation itself is a graph. It's a series of one point to another. And so if you're interested in using the logging, we actually have something that's NeoDash where you can do natural language to like charting. So if this is new for you, there are sort of lower barrier ways to get some of these analytics available to you. So one of the things that you want to look at is you want to start by looking at what is the conversation length. As expected, it's going to have a long tail on it. Most of our conversations seem, a few prompts and responses. And that means for us, we're working specifically with our users where we want them to get the answer relatively quickly, right? They've come to this particular use case because they have a question about graph data science, and we want them to get the answer and move on. So when we see these longer conversations, those are ones that you'll want to dive into. Was someone realizing that they wanted to go into another direction, or did it take them a really long time to get the answer they were looking for? This one has to do with the response time. So we also looked at what those response times are for each as the conversations got longer. Obviously, we see the times get longer, mostly because of the context window, as we said. And so it makes sense that those will increase over time. But different things will affect that, your limit, your context window, conversation memory, etc. So what does it mean to have all these items, and how can we actually get better at using this graph-based analysis of these context documents? So like we said before, in each conversation and in each message, there is a context document attachment based on that use. And so by logging these conversations, you can now start to look at the structure of the graph to understand how are people moving around. So in this case, the dark red is the actual response, and the light pink are the context documents that came in. And we can see that there's a few questions, say, on the outer edges, right? So we see these where they're sort of the satellite pieces. In those situations, what we're seeing is those context documents came into this one response. But what we see in the center is there's a lot more interconnection. And so this is telling us that these conversations here are repeated conversations. These are the documents that are being hit more often. And so when you're looking at a graph, I always encourage you to look at it with what I call the soft eye, which means don't go into too much detail about what's in there, but what is the shape telling you, right? If we had one cluster and another cluster, it's going to tell us that there's two areas where people are asking questions most likely. And then some of the things that are on the outer edge, they're not the most common questions and not the most common context documents. So again, the soft eye can be really helpful in seeing those natural clusters and giving you a visual understanding of how folks are working with your application. So one of the things that we looked at to see if we were getting relevant context is we wanted to see what were the most frequently used documents. For us, we see degree centrality, which is a big question, and then the actual connectors. So centrality is one of the most common algorithms that folks use. And how good is a database if you can't get your information into it? So the connectors are a really important piece. And this makes sense, right? The other thing that we looked at is we looked at the frequency of the communities of information. Obviously, it makes sense that the top one is our documentation. Most of the answers, if you're looking for something, are hopefully in our documentation. If they're not, we have a much bigger problem. There are some people we need to talk to. And then the second most frequent one that we had was actually the blogs from Tomasz Bratanek, who's one of our experts. And if anybody's ever read any of our LLM and GenAI work, you'll definitely have read his pieces. So that's not necessarily a surprise to us either. But again, it's not just enough to have a database for your RAG application. It's important to look into how is it being used, what are people seeing. So the next thing that we can also look at is we can also look at the actual responses. So this is where we take the next step. So initially we had each of those responses connected to the context documents. But now we can start to say, how do the responses relate to each other? And we can run similarity on those responses. So again, let's take the next step. We got these series of responses. Are they very similar? Are we getting the same kinds of answers? Are people working in one particular area? So we can see on the right-hand side here, we have each of the responses, and we've created, again, this similarity, the cosine similarity, between these responses. One of the ways that this can be helpful to you as a developer is you can look to say, if there are common responses, can we actually use the predefined responses or that response area so that we can optimize the speed with which we can respond? If we know that we've got a cluster of responses that are very similar, do you want to potentially pre-feed some of those into your application to have those answers already generated? So it's just something to consider, but this allows you to look and see, are we getting consistent answers and how can we leverage these in other ways? Now, just like we had our 2D viewing of the context documents, now we're looking at the 2D view of these responses. And so initially, we didn't want a lot of redundant documents where we have those clusters of information. But in this case, we actually do want them to be very similar. We want to get a similar response when people ask similar questions. We want to have that consistency of output so that the user experience is going to be reliable, it's going to be clean, and it's going to be relevant. This is telling us that we've got these areas of understanding of what people are getting back as information. And again, this is an interesting way. This is where you hand it off to your product people if it's a product RAG application, or your marketing folks if it's consumer product information. And you can say, these are the kinds of answers that people are getting. This is the documents that we're hitting. And then they can go and do what they do with it. But as developers, what we want to see is we want to see this consistency with these responses. All right. So we can look at these communities of responses, and now we can start looking at you'll see all the way on the edge, we've got the ratings. So for this community of responses that we had, were people satisfied with those answers? Right? We can see, community 14,725, we've got 15 good ratings and only 2 bad ones. That's not so bad. But when we look at the second row or the bottom row, the numbers are not as good. We're getting kind of met answers. And this is another way to say, what does that response look like? And then you go to those context documents and you can say, what is it that's not in the data that people need? They're not getting the answer they want. How does it relate to the specific context document? How does it relate to the response that they're getting? And how can we improve the underlying data set in order to get a better output and a better experience? Because it's not just enough to get an answer. We want to make sure that we're giving the right answer and that we don't have holes in our data set. That's one of the most common things that I've seen that people don't necessarily realize when they're putting their data in, is really figuring out when something is missing. And this is a really good way to go about finding those holes in your data sets. We looked at the pages with the highest page rank score. Page rank score means how important is this and how relevant is this within that document. And these are on a couple of things. They happen to be GDS. Network X, for any of the data scientists in the room, was probably the first graph you ever used in Python, and our PyTorch. So ultimately what we want to say is that this grounding with the graph allows you to do a few things. One, it's going to give you better answers. And two, it's going to allow you to dive into the data that you have and build something that's not going to be good just for today, but is also going to help you build something that can be maintained. Because ultimately, that's what we're looking for. We want to have a way that we can actually dive in and maintain the applications that we are using. Does anybody want to see what some of this looks like? Anyone? Yes? All right. Officially, this is the end of the talk for now. But what I want to be able to do is show you a couple of the things that we have here. So, we have we've got a few different demos that you can look at. This one happens to be using SEC data, which is the filings with the New York Stock Exchange when you have items. So in this particular case, we can see that we've got a company which had a filing that company might be owned by an asset manager. So here, manager means asset manager, and asset managers own many different stocks, and then each of those may have an address. And so what we want to think about is when we're building a RAG application with just vectors, and we're hitting those, that's all we can get. We get that chunk, we get that vector, that's all that comes back. But when you're using a graph, what it will allow you to do is you're going to come up to that chunk of that document based on that cosine similarity, but then you can add in additional pieces within your application that says, okay, when I hit that chunk, I want to also bring in information about the company that filing was for, and potentially any asset managers that own that. And so what we have here is we're looking at some of the answers. So if we're looking at, this question is, which asset managers are impacted by lithium storage? And let me see, we'll run this for you. So this just shows you what's in here. Any of the demos that we're showing today, again, are all available. They're all open source on the Neo4j GitHub. It takes a little, it's all about connecting. While it's running, does anybody have any questions? Has anybody been worried about if their data set that they're using for their RAG application is actually any good? Or has anybody asked you? Yeah, right? How have you been tackling it so far?
Not very well.
Okay. Do you think some of this might be helpful?
I'm hoping so.
Yeah, okay. Well, if you have any challenges with it, you reach out to me and I'll help you out. All right. So in this case, what we see is we asked which asset managers are impacted by the lithium storage. And it's going to give you an answer that's somewhat general because, again, it's only able to access the documents at that chunk level from the filing. The vector doesn't know that there's a relationship all the way up to the asset manager. And so here it lists, based on the context provided, a summary of asset managers that are impacted. It'll show a few, but these are all the companies. They're not the actual asset managers. But when we use the graph and we actually attach those structured pieces to the unstructured, we can clearly see that Tiger Management and Berkeley are mentioned as asset managers for multiple companies whose SEC filings discuss risks and opportunities related to this lithium storage. So what it's giving you is it's giving you not just what's in the unstructured piece itself, but whatever the relevant structured piece is that can be informative. Vectors are really bad at anything that's going to be an aggregation, right? Because it's going just to these few things. And so it adds that to you as well. We also have, this is the actual agent Neo that we used. And in this, we can say whether we're using grounding or not. And so this is just another way of testing. So if I turn grounding off, it's going to give me just the LLM answer. And if I turn that on, it's going to actually pull in those context documents. So we can ask, I'm trying to think of a good one at the moment on the fly. But again, all of these demos are available to you and you can use them for your own use cases. My point in all of this is that while the vector database and the basics of RAG are readily available to you, I just want to encourage you to consider what happens after the vector and what is available to you beyond the vector. And that's it for now. If anybody wants to see any more of these demos, please come find me. I will be here all day. And I appreciate all of your time and attention. And to everyone watching online, thank you for spending time with us today. Thank you so much.